Okay, solubility equilibria. So back in Chapter 4 in Chem 1A, you learned some solubility rules. We identified things as being soluble or insoluble. But now we're going to look at degrees of solubility. So, as with most things, it's not absolute. You're either soluble or you're not soluble. There's this whole continuum. So when a substance dissolves, that is an equilibrium process. So here we have calcium fluoride solid. As that dissolves, it forms calcium ions and fluoride ions. But while that is occurring, calcium and fluoride ions can also be reprecipitating to form the solid again. And so this is definitely an equilibrium process. So we can write an equilibrium constant expression for this. And for this equation, it's going to be calcium concentration times the fluoride concentration squared. Normally we would divide by the reactant concentration, but it's a solid. And we don't include solids, liquids, and gases. Well, solids and liquids, sorry. We don't include solids and liquids in our equilibrium expressions. So the equilibrium expression is shown here, and that's given a special name. It's the solubility product constant, because it's the solubility, so KSP, solubility product constant for that ionic compound. When we talk about solubility, it's the quantity of the compound that will dissolve, and we have to specify how much of the liquid, how much of the solvent. So you'll see tables, and they may show how many grams will dissolve in 100 grams of water, and that's a way to specify solubility. We're going to look at molar solubility. So molar solubility has the units of moles per liter. So it'll be moles of the solid that dissolve per liter of solution. And this can be calculated from KSP. It's important to note that KSP is not the molar solubility. Molar solubility is how many moles dissolve per liter. KSP is an equilibrium constant. It has a single value at a given temperature, but at a different temperature, it will have a different value. The molar solubility can have different values in different solutions at the same temperature due to the common ion effect. So if you mess with the acidity or you add some other common ions, you can affect the molar solubility even though the KSP, that equilibrium constant, hasn't changed. So in order to find molar solubility, we have to do equilibrium calculations. So let's look at silver chloride, which we generally think of as being insoluble. And its KSP is actually very small, 10 to the minus 10, but it's not 0. So silver chloride will dissolve to a small extent. We can calculate the molar solubility from the KSP value. So we look at the equation for silver chloride dissolving. It forms silver ion and chloride ion. So then we can write the expression KSP is going to equal the silver ion concentration times the chloride ion concentration. Well, initially, we're going to have none of those ions present because we've got pure water and we're going to put some of the solid in. Initially, we have no ions present. So then the change for both will be the same. We'll call it S. So plus S are equilibrium concentrations. Each of them is S. So this is equal to S times S, also known as S squared, right? So KSP has the numerical value, 1.77 times 10 to the minus 10, and that is equal to S squared. So that means that S is the square root of KSP. So if we want to get rid of that square, we take the square root of both sides. So the molar solubility of silver chloride is 1.33 times 10 to the minus 5 moles per liter. It's pretty small, but some of it does dissolve. Yeah.
So then we'll need to remember that KSP is constant?
Yes.
Even though it could change at other temperatures?
It can change at different temperatures. It's just,
Like a
it's the
standard-
same idea as the equilibrium constants, Kc and Kp that we were looking at, and Ka and Kb, the ion product constants for acids and bases. It's just for dissolving an ionic compound. So it's same everything. Yeah.
This follows the same rule that like you didn't put AgCl in the denominator because it's a solid, right? It's
Correct.
a solid level.
Yep. So this equilibrium expression is written the same way that we've done all the others. I didn't include this in the denominator because it's a solid. And a solid's concentration can't change. You either have some solid or you don't have any solid. But its concentration is the same. And that's the same for a pure liquid. So water is a liquid, and so in an aqueous solution, we can't say that the water's concentration changes, right? Any other questions? KSPs are not something that you memorize. Here's a table from your textbook showing a bunch of different KSPs. And looking at them, you can see that they vary significantly here. Copper 2 sulfide, 10 to the minus 36, that's pretty insoluble. And some of the others, lead chloride is 10 to the minus 5. That's probably a little more soluble. So you just look them up. Let's calculate the molar solubility of iron 2 hydroxide in pure water, and we're given the KSP. So we're going to start out by writing a balanced chemical equation for the dissociation of iron 2 hydroxide. So we've got iron 2 ions that are forming, and we've got hydroxide ions. And there's going to be 2 hydroxide ions. So there's another skill from 1A coming back. You need to be able to separate these into the ions with the charges and balance the equation. So we can make an ice table for this. What are the initial concentrations of iron and hydroxide? 0. Because we're putting the solid into pure water. And then how are they going to change? They're going to increase, and we'll use S instead of X. And so sulfur, that's S. Iron is going to be plus S, right? And what's the hydroxide? Plus 2S. Okay, so then at equilibrium, we've got S, and we've got 2S. So let's write the expression for the equilibrium. KSP equals the iron concentration times the hydroxide ion concentration squared, right? So if we put the S's in there, we have S times 2S, that quantity squared. So that's going to be 4S cubed, right? There's just some little algebra here. And we know what KSP equals is 4.87 times 10 to the minus 17. So now we have an equation we need to solve for S. So if I divide this side by 4, I can get rid of that. And then to get rid of S, the cube on S, I need to take the cube root of both sides. So I'm going to take the cube root of this whole thing, and then that'll get rid of my cube on the S. So on the TI-36X Pro, if you want the cube root, you put in 3 first, and then there's a root with a square button. You press that one, and then you put in the stuff underneath. 4.87 times 10 to the minus 17 divided by 4. 2.30 times 10 to the minus 6.
What did you get?
2.30 times 10 to the minus 6. Yeah. Anybody else get that?
You got what?
2.3 times 10 to the minus 6. Okay. Heard at least 2 other people got that. So we have understanding the chemistry and what we're supposed to be doing, and then we also have understanding how to make your calculator do what you want it to do. And you have to master both of those. Let's look at the molar solubility of... Oh, wait. We're calculating KSP from the molar solubility. So we're given the molar solubility of silver bromide, is this, and we're asked to calculate KSP. Well, let's just think about this. Might be a good idea to start out with the chemical equation describing how this dissolves. So we're going to have silver ions and bromide ions. So molar solubility, what's that telling us? It tells us what S equals. It tells us how many moles of this dissolve per liter of solution. So we don't have to do the ice table thing, but it might be helpful. This one's simple, but if you get one that, like iron 2 hydroxide, where you have 2 hydroxides, then it can become a little more complicated. Initial concentrations were 0, and the change is that each of these increases by S. So then at equilibrium, the concentration of each of these is the same as the molar solubility. KSP equals the silver ion concentration times the bromide ion concentration. And we've determined, looking at this little ice table, that each of those is equal to the molar solubility. We've got S times S, which is S squared. And we know what S is because it told us in the problem 7.3 times 10 to the minus 7. So KSP is that squared. Any questions? Yeah.
You know when you're, let's say there's another, it's like a double reaction on them. Like, you know, there's spectator ions, are they going to be considered in the calculation as well, or not?
In dissolving a pure ionic compound, there aren't going to be any spectators. It's a good question. Yeah.
So then, so molar solubility and KSP are not the same. You can find molar solubility through KSP.
You can find one from the other.
But the molar solubility is the change. Well, not the change in. So like in this case, like the products, the product of the product.
So the molar solubility is going to be, for anything with a coefficient of 1, the concentration of that ion will be equal to the molar solubility. But if you have an ion with a coefficient of 2, its concentration will be twice the molar solubility. Because for every mole, it releases 2 moles of that ion.
And then for the product of the however many products there are is the total molar solubility. Like so how we multiplied the S times S.
Well, to find KSP, you have to multiply
Yeah.
these together to get KSP.
And then
Yeah.
KSP. Okay.
Yeah. Any other questions? So molar solubility and KSP are related. We can find one from the other, but you can't just look at KSP and say, oh, well, this one's more soluble than that one. Because if we look at magnesium hydroxide and iron 2 carbonate, the KSP of magnesium hydroxide is lower, smaller, than for the iron carbonate, but magnesium hydroxide has a larger molar solubility. And the reason is stoichiometry. Because when this one dissolves, it forms 3 ions. When this one dissolves, it forms 2 ions. So the KSP expression is different. And that affects the molar solubility relative to the KSP. If we compare these two that have the same stoichiometry, 2 anions to 1 cation, and we look at the relative KSP values, we see that it matches up with the relative solubility. A larger KSP gives a larger solubility if the stoichiometry is the same. If the stoichiometry is not the same, you really can't compare them. It's like comparing apples and oranges. Or plums and peaches.
Would there ever be a case where they are the same, or
Where what's the same?
the KSP solubility, or no? Like, if,
Well, the KSP and the solubility cannot be the same. Yeah. Unless that was 1. If it was 1, I guess it could be the same.
but like even like something like H2O, that wouldn't be it because you just have OH and have H. I get it.
Yeah. And you can't talk about H2O dissolving because what does it dissolve in? Okay, so how can the molar solubility be different at the same temperature if KSP is the same? Well, if you have other things in solution. So if we have a common ion in solution, that's going to reduce the solubility of the ionic compound. So if we're dissolving calcium fluoride, it forms calcium ions and fluoride ions. If we're dissolving this instead of in pure water, in a solution of 0.1 molar fluoride ion, the fluoride ion is going to cause the equilibrium to shift to the left. Look, I've got 2 pointers now. So adding some fluoride will cause the equilibrium to shift to the left. That reduces the molar solubility. KSP is the same, though. Any questions? That make sense? Let's look at how that would work. Calculate the molar solubility of calcium fluoride in a solution containing 0.250 molar calcium nitrate. Here we do have a spectator ion. What's the spectator? Calcium is not a spectator. It's a nitrate. So we're looking at the solubility of calcium fluoride. So calcium fluoride solid dissolves and forms calcium ions and 2 fluoride ions for every formula unit that dissolves. That's an excellent question. How do you know that CaF2 is a solid? What kind of a compound is it? Ionic. Ionic compounds have very high melting points. So yeah, an ionic compound, it's very safe to assume, is a solid at room temperature. Yeah. Because it's ionic bonds that hold it together. Whereas with molecular compounds, some are solids at room temperature, some are liquids, some are gases, because they're held together by intermolecular forces, which are much weaker than ionic bonds. So ionic compounds will be solids at room temperature. Excellent question. So making our ice table, what's the initial concentration of calcium ion? Is it 0? No, it's not 0, because this solution contains 0.25 molar calcium nitrate. So it starts out being 0.250 molar calcium ion. The initial concentration of fluoride is 0. I don't like it when people's conversations in the hallway end up on the YouTube video. So this is starting out non-zero. This is starting out at 0. The change is going to look the same. We're adding to both of them. We're adding S to the calcium because its coefficient is 1. What are we adding to the fluoride concentration? 2S. Because each unit of CaF2 that dissociates forms 1 calcium and 2 fluorides. So for every 1 mole of calcium fluoride, we end up with 3 moles of ions, because they come apart. It's not that we're making new things. They're just coming apart. So now equilibrium is going to be 0.250 plus S. And for the fluoride, it's just going to be 2S. KSP has a value 1.46 times 10 to the minus 10. And that equals the calcium ion concentration, 0.250 plus S, times the fluoride ion concentration, 2S squared. Could we use the S is small approximation? We can try, right? Because we have a relatively large number plus S. So let's try S is small. That'll give us 1.46 times 10 to the minus 10 being equal to 0.250. And I'm going to multiply that out. That's going to be 4S squared. So S would be the square root of 1.46 times 10 to the minus 10 divided by 0.25 and divided by 4. (1.21 times 10 to the minus 5). How do we know if it's okay to use X is small? We'll take what S came out to be, and we're going to divide it by what we added it to, or subtracted it from. So I'll take that number, divide by 0.25, multiply by 100 to make a percentage, 0.0048%. Yeah, S is plenty small. So this is the solubility. Yeah.
Can you explain why calcium starts off with 0.2?
Yes, I can explain why calcium starts off with 0.25. We are dissolving the calcium fluoride in a solution that contains 0.25 molar calcium nitrate. So instead of dissolving it in pure water, we're dissolving it in a solution that already contains calcium ions. So that's why we're starting with 0.25. Those did not come from dissolving the calcium fluoride. Those came from a different source. It came from calcium nitrate. Does that help? And that's what's called the common ion effect. What would the solubility be without that ion, that extra calcium ion? Yes?
Oh, no, I'm not sure to finish that question after you finish.
Okay. What's the solubility without that? Yeah, it was 4s cubed, right? I think we did this one, but I don't remember what it was, so I'm going to do it again. - 1.54 times 10 to the minus 5. This is the molar solubility in pure water. This is the molar solubility in this solution that already contains some calcium ions. It reduces the amount that will dissolve.
So I'm kind of confused on how I get how it came from the calcium nitrate, but how do we know that is the molarity shared between calcium and nitrate?
Okay, that's a good question. So calcium nitrate, we should really consider what is the solubility of calcium nitrate. So if you remember, which I don't blame you at all if you don't, the rules of solubility up at the top, nitrate compounds are soluble, no exceptions. So calcium nitrate is very soluble in water, and so we can assume that it dissociates completely here. This is not a saturated solution. And so there are 0.250 moles per liter of calcium ions and 2 times 0.250 moles per liter of nitrate ions. Because it's like a bicycle, and you take it apart and you get 2 wheels and 1 frame. If you take a dozen bicycles apart, you get a dozen frames and 2 dozen wheels.
Okay, so right there, that you're going to multiply times molarity times 2 because nitrate would have a coefficient of 2. Going back to that problem you did right there, right behind you, review number 2, we didn't multiply the coefficient of SO2 towards the actual molarity there. So what's the difference between
But the 2 comes in here in the change.
Oh, so you just did it right there, not right there.
So in this problem, it was saying that we calculated the concentration of SO2. This isn't an ionic compound. We're not looking at ions that have separated.
Oh.
If we look at calcium nitrate and say 0.25 molar calcium nitrate, and we want to know the concentration of nitrate ions, then we do have to multiply by 2. But we're multiplying by 2 because of this subscript, not because of a coefficient in the equation. Any other questions? pH also can affect solubility. Let's look at magnesium hydroxide. So magnesium hydroxide forms magnesium ion and 2 hydroxide ions. If we have a high hydroxide ion concentration, that's going to cause the equilibrium to shift to the left and reduce the molar solubility of magnesium hydroxide. If we have an acidic solution where we have a lot of hydronium ions, the hydronium ions will react with the hydroxide, which reduces the hydroxide ion concentration and will cause the equilibrium to shift to the right. So in an acidic solution, this will dissolve at a higher rate. The molar solubility will be higher. Any questions? So in general, the solubility of an ionic compound with a strongly basic or weakly basic anion will increase with increasing acidity. Common basic anions would be hydroxide, sulfide, and carbonate. So these will be more soluble in an acidic solution because the acid reacts with the basic anion. rainwater is naturally slightly acidic due to dissolved CO2. And so it can dissolve limestone, which is calcium carbonate, as it goes through the ground. And this can result in huge underground caverns where slowly, over long periods of time, slightly acidic rainwater dissolves away the calcium carbonate and forms some really cool structures. Then you've got that water that's dripping and it's saturated with calcium carbonate, and it drips down, and the water evaporates and leaves the calcium carbonate behind as you get the stalagmites. The stalactites are formed the same thing, they just come down from the ceiling. Any questions? Okay, so this question, which compound, iron 2 carbonate or lead 3 bromide, is more soluble in acid than in base, and why? Well, we could just guess, but that's not a good idea. Let's look at what these things form when they dissolve. So we're going to get, no, not iron 3, it's iron 2.
Ms. Kay,
Yes?
why does the oil from your hand ruin a cave? They tell you if you go into the caves, like the organ caves, for instance, they're all green because people used to touch the side.
Why does the oil from your hands affect a cave? So it makes it green, like with algae? I'm guessing that it gives the algae something to eat.
So it no longer focuses on the building, it focuses on the algae.
So the presence of the oil would allow the algae to grow, where it wouldn't grow just on the bare calcium carbonate. That's my guess, off the top of my head. And then we're going to get carbonate ion. And for lead, PBBr3, that's strangely difficult to say. Okay. So these are the ions that are going to form. So whereas this is, which one of these is going to be more soluble in acid than in base? So an acidic solution, that means we've got hydrogen ions, extra hydrogen ions, right? Are extra hydrogen ions going to react with carbonate? Yeah. If we get 2 hydrogen ions and a carbonate ion, that forms carbonic acid, which is a weak acid. But carbonate is also unstable and decomposes into water and carbon dioxide gas. Dioxide, not trioxide. So the acid with the carbonate is going to form water and carbon dioxide. That is essentially taking away the carbonate as it dissolves, right? If we're removing product, that's going to shift the equilibrium to the right, causing this to dissolve more than if we weren't taking away carbonate ion. Is acid going to do anything to bromide ion? No. Bromide ion is the conjugate base of a strong acid. It is not going to react with hydrogen ion. It's just going to sit there. And so this is not going to be affected by acid. So the iron carbonate will be more soluble in acid because the anion is the conjugate base of a weak acid. Any questions? I can almost hear the wheels turning in your heads. It's kind of this very faint, scratchy, squeaky sound.